Hello everyone, welcome to course study on solid mechanics. In today's lecture, we are going to derive the flexural formula for pure bending. We already discussed the concept of pure bending. Remember that in case of pure bending, the beam is subjected to only bending moment. It does not subjected to any axial force or the shear force. Now, let us consider one small portion of the beam which is subjected to a simple bending. Remember that under the action of simple bending, the beam will bend into the arc of the circle so that it will have a radius after the bending action. Now, as shown in figure, let AB and CD are the two vertical sections which are to be considered in a beam. This is the small portion on which we have to concentrate for deriving the flexural formula. Also, from figure NA is nothing but the neutral axis of the section of the beam. It is already shown in the figure. EF is equal to the neutral layer at the neutral axis. Remember that EF is the neutral layer at the neutral axis. We have already discussed the concept of neutral axis. It is an axis which passes through the neutral layer and it is perpendicular to the cross section of the beam. Now, dx is nothing but the length of the beam between two sections, that is AB and CD. Let us consider one layer GH, this GH at a distance of y below the neutral layer EF. Therefore, it will be equal to dx. Now, as dx is equal to the length of the beam between section AB and CD, the same length or the same layer we have considered which is equal to GS. Therefore, remember that the original length of neutral layer EF, from you have to concentrate on figure, original length of the neutral layer is equal to original length of layer GH, which is equal to dx. So, from figure we can say that EF is equal to GH is equal to dx. Now, as the beam is subjected to pure bending, therefore we have the arc of the circle. Therefore, this figure shows the bent portion of the beam when it is subjected to a simple bending. From figure, after bending we have section AB and CD will be now section A-B- and C-D'. Remember that due to the action of pure bending, the beam will bend into the arc of the circle. Therefore, our original section AB and CD will become A-B' and C-D'. In the same manner, layer GH will increase to G'-H'. This is the very important concept we are going to discuss over here. Similarly, layer GH will increase to G'-H'. It means that if we concentrate on a neutral axis, then the portion which is above the neutral axis, then it is in compression, and the portion which is below the neutral axis, it is in tension. But when it is subjected to bending action, the portion which is below the neutral axis, it will get stretched to its original length, and the portion which is above the neutral axis, it will get decreased from its original length. Therefore, from figure you concentrate on figure. Similarly, layer GH, if you concentrate on layer GH which has a distance equal to EF, which is equal to dx, this layer GH will increase to G'-H'. It will increase to G'-H' means it is below the neutral axis. Therefore, the stretching of that particular layer will take place. Therefore, G'-H' will be greater than GH. This is very important concept in case of pure bending. In case of pure bending, the layer which is above the neutral axis, it will get compressed, and the layer which is below the neutral axis, it will get stressed, or it will be in tension. So, the layer GH will become G'-H'. This is the increased length of GH. The neutral layer EF will now become E'-F'. You can see from the figure, the neutral layer EF will become E'-F', but as it is the neutral layer, there will be the no change in its length. The name itself indicates that what is neutral layer. Neutral means there will be the no increment into its length or no decrement into its length. It will remain as it is, just as of original. Therefore, EF is equal to E dash F dash, which is equal to dx. So it will remain as it is just before of bending. Now A dash B dash and C dash D dash are meeting with each other at center O. If you concentrate on figure, you can observe that A dash B dash and C dash D dash will meet at a center O. This is the center O. Therefore, as it will meet at the center O, we have R is equal to the radius of neutral layer E dash F dash. Therefore, the radius of neutral layer E dash F dash is equal to R, which is known as radius of curvature. Also, from figure, theta is nothing but the angle made by A dash B dash and C dash D dash at center O. Therefore, the distance of layer G dash H dash from the neutral layer is E dash F dash is Y dash. If you concentrate on figure, the layer G dash H dash will be located at a distance of E dash F dash by an amount of Y. Therefore, the length of neutral layer E dash F dash is equal to R theta. E dash F dash is nothing but it is the arc of circle, and as we know that E dash F dash has a radius equal to R and it make an angle of theta. Therefore, the arc of circle has the length equal to R theta. Therefore, the original length of the layer GH is equal to the length of neutral layer EF, which is equal to the length of neutral layer E dash F dash, which is equal to R theta. Remember that in this equation we have calculated the value of E dash F dash by the formula arc of circle. E dash F dash is equal to R theta, but as we know that it's a neutral layer, so neutral layer it does not have any change in its length. Therefore, E dash F dash is equal to EF, which is equal to R theta. You have to remember this is very important concept while deriving the flexural formula for the pure bending. Therefore, if you concentrate on to the figure, the length of layer G dash H dash will become R plus Y into theta, because we have E dash F dash is equal to R theta, and if you have to find out the value of G dash H dash, then R plus Y into theta, it will give you the length of G dash H dash. Now, if you observe, the change in length of the layer GH is equal to length of the layer G dash H dash minus original length of the layer GH. From figure, you can observe that the change in length of the layer GH is nothing but the length of layer G dash H dash minus original length of the layer GH. Now, as we have already calculated the length of layer G dash H dash, which is given by R plus Y theta, this equation we have to use to calculate the length of layer G dash H dash. R plus Y into theta minus the original length of the GH is nothing but it is R into theta. Therefore, after rearranging or cancelling the same term, we have change in length of layer GH is equal to Y into theta. This is the value of change in length of layer GH, because we have concentrated on a small fiber of our beam, and for that small fiber we have to calculate the value of sigma, means stress, the value of strain. So the change in length of layer GH is given by Y into theta. You have to remember this equation. Once you know the value of change in length of layer GH, we can easily find out the value of strain in layer GH. Therefore, we have the strain in the length of layer GH is equal to change in length of layer GH upon original length of layer GH. And as we have calculated the value of change in length of layer GH, we have Y theta upon R theta. Therefore, the strain in length of layer GH, which is denoted by the letter epsilon, is given by y upon r, because theta theta will get cancelled in this equation. So we have the final strain in length of layer GH is equal to y upon r. This is the value of strain which we have calculated for the layer GH. And for the same layer we are going to calculate the value of stress, and that is our aim to find out the flexural formula. Now we are going to calculate the value of stress for the layer GH. This is the layer on which we have concentrated our entire derivation. Now all of you know that Hooke's law. Hooke's law is nothing but within the elastic limit, stress is directly proportional to strain. Mathematically, it is given by sigma is equal to E into epsilon. Therefore, I have sigma is equal to E into epsilon. If I put the value of epsilon from this equation, I have sigma is equal to E into y by r. Now, for a given equation, the value of Young's modulus of elasticity of any material always remain constant, and the value of r, the radius of curvature for a given bending moment, it always remain constant. So as E and r is constant, it means that stress is directly proportional to y. Therefore, the value of stress, it is a function of y. If y is equal to 0, now all of you know that this y is nothing but it is the distance of G dash H dash or GH from the neutral axis. Now if our y is equal to 0, then the value of stress will be equal to 0, because all of you know that stress is directly proportional to y. Now if y is 0, it means that our value of stress is also 0. But as the value of y increases from the neutral axis, the value of sigma also go on increasing. Therefore, at the extreme fiber, we have the maximum value of the stress, whereas at the neutral axis, we have the minimum value of the stress. This is the very important concept for the for deriving the flexural formula and for the stress value. Remember that sigma is directly proportional to y. After rearranging equation, I have sigma by y is equal to E upon r. It means that this is the first step of deriving the flexural formula. In the next lecture, we will discuss about the concept of moment of resistance and the concept of section modulus. We will stop here. Thank you.